Welcome back, students. So in the previous video we have discussed what are the experimental observational facts about the photoelectric effect. So now let us recall all those facts once again. So why? Because we need to study how does the classical mechanics fails to explain the phenomena of photoelectric effect. So the first experimental observational fact is the photoelectric effect is an instantaneous process. So that is, the time lag between the incident radiation and the emission of the electrons is about 10 to the power of minus 9 seconds. So therefore we say that the photoelectric effect will be an instantaneous process. So the second observational fact about the photoelectric effect is, that is, if the frequency of the incoming radiation nu is greater than the threshold frequency, that is the minimum frequency of the incoming radiation. So as the intensity of the incoming radiation increases, or if you change the intensity, or if you increase the intensity of the incoming radiation, that is the photoelectric current also increases. So that is, if the frequency of the incoming radiation is greater than the minimum frequency for a given metal, if you increase the intensity, so the photoelectric current also increases. So this is the second observational fact about the photoelectric effect. And the third observational effect is that for any metal there is a minimum frequency, there is a concept of minimum frequency for any given metal. So that frequency is what we call it as the threshold frequency. So that is, for any given metal there is a minimum frequency of the incoming radiation below which there is no photoelectric effect takes place, or there is no emission of the electrons by the metal surface. So this minimum frequency is what we call it as the threshold frequency. So that will be usually indicated by nu naught, and the corresponding wavelength will be known as the threshold wavelength, and that will be indicated as lambda naught. Okay. So for every given metal or for any metal, there is a minimum frequency of the incoming radiation, so which is known as the threshold frequency, below which there is no emission of the photoelectrons, or there is no photoelectric emission. So this is what we call it as the threshold frequency, which is indicated by nu naught. So and the corresponding wavelength will be known as the threshold wavelength, that is indicated by lambda naught. So now the fourth observational fact is that if you increase the frequency, that is, if the frequency increases, okay, of the incoming radiation which is greater than the threshold frequency, as the frequency increases, the kinetic energy of photoelectrons also increases. So the fourth observational fact is, that is, if you increase the frequency of the incoming radiation, or the frequency of the incoming radiation increases greater than the threshold frequency, the kinetic energy of the photoelectrons also increases. So this is a fourth experimental observational fact. And the fifth observational fact is that, is, as if you increase the negative potential of the anode plate or the collector plate, so as you increase or you make more and more negative of the anode, that is, if you increase the negative potential of the anode, so what happens? The stopping potential also increases. So these are all the observational facts about the photoelectric effect. So now let us see how does the classical mechanics fail to explain these phenomena if you consider the classical ideas. Okay. So now let us see. So that is what is the failure of classical mechanics in order to explain the phenomena of photoelectric effect. So here we will use that light is a electromagnetic wave, that is electromagnetic transverse wave. So this is the idea of classical mechanics about the light. Okay. So that is, we are treating light as an electromagnetic transverse waves, that is, it consists of electric field vectors and it consists of magnetic field vectors. So according to electromagnetic wave theory, okay, so light the view of the classical mechanics about the light is the electromagnetic wave nature or electromagnetic transverse wave, which is consisting of both electric and magnetic fields which are perpendicular to each other and also perpendicular to the direction of the propagation of the wave. Now let us see what was the idea of classical mechanics to explain the phenomena of photoelectric effect. See here, let us compare the observed phenomena and what explanation will the classical mechanics give about this experimental observation. So according to experiment, we have that we can say that the photoelectric effect is an instantaneous process, but here the classical mechanics says there is the time lag between the incident radiation and the emission of the electrons will be about few hours or few days after the radiation incident for the electron to emit from the metal surface. That is, if we have a metal surface and if radiation is made to incident on this metal surface, after the radiation is incident on the metal surface, it takes a few hours or it may take few days for the electron to come out of the metal surface. But experimentally what we are saying, as soon as the radiation is incident on the metal surface, there is emission of the electrons by the metal surface. So here the classical idea, that is the light is nothing but electromagnetic wave. So this fails to explain the first experimental observational fact. Okay, so that is, it is not an instantaneous process according to classical mechanics. Now let us see how does the classical mechanics explains the second observational fact. So in the second observational fact, here we say that that is, if the frequency of the incident radiation is greater than the minimum frequency, then only we can see that there is photoelectric current or there is emission of photoelectrons or photoelectric emission takes place. But according to classical idea, it says that there is no concept of threshold frequency or minimum frequency. According to classical theory or the classical mechanics or according to electromagnetic wave theory, it says that there is no concept or there is no need of minimum frequency. That is what we call it as the minimum frequency. It is not necessary to for the light to stop. Okay, so according to the experimental observational fact, we have that for a frequency which is greater than threshold frequency, as the intensity increases, the photoelectric current also increases. But classical mechanics says, that is, if you consider light as an electromagnetic wave, so there is no need of or there is no concept of minimum frequency, that is, there is no such frequency, that is threshold frequency required for the emission of the photoelectric effect. So therefore again it contradicts the experimental observations. Now what is the third concept, that is in case of experimental observation, is there is a minimum frequency for each and every metal. Okay, if the frequency of the incoming radiation is less than that particular frequency, there is no emission of photoelectrons. So the answer or the explanation of the classical mechanics about this particular experimental observation fact is that, so there is no need of minimum frequency. A high intense beam, okay, high intense beam of light is enough to take out the electron from the metal surface. That is, according to classical theory or according to electromagnetic wave theory, if we have sufficiently high energy beam or sufficiently high intense beam of light is more than enough to take out the electron from the metal surface. That means that, so we know that the intensity is directly proportional to amplitude square. So amplitude means it is nothing but energy. Okay, so more is the energy, more is the amount of electron that we can take out from the metal surface. That means that whenever radiation or incident on the metal surface, the energy of the radiation will be distributed over the entire wavefront, or it will be distributed over the entire wave of the electromagnetic light. Okay, that is electromagnetic wave. So whenever we have energy which is distributed over the entire wavefront or over the entire wave, so when this falls on this metal surface, so this energy of the incident radiation will be absorbed equally by all the electrons. Okay, so when the electrons gain sufficient energy, so what happens happens? The electrons comes out of the metal surface. So this is the explanation of the classical theory for this minimum concept, that is the minimum frequency concept. Now as the frequency increases, the kinetic energy of the photoelectrons also increases, but the classical mechanics does not give any idea about the kinetic energy of the photoelectrons, just it gets stopped. That is, it says that high intense beam of light is more than enough for the emission of the photoelectrons, and it also says that why there is a time lag, okay, that is why it takes few hours or few days for an electron to come out of the metal surface after the incident of the radiation. Means let us consider a metal surface, and here we have the radiation which is incident on it, okay. Now so there is certain energy or there is certain intensity for the incoming radiation. When this intensity or when this radiation which is having a certain intensity is made to fall on the metal surface, okay. So the energy of this radiation or the incoming radiation is distributed for all the electrons, okay, or that is the electrons which are present on this metal surface. So whenever there is a continuous radiation which is incident on the metal surface with sufficiently high intense beam, after absorbing continuously the energy by the electrons which are present on the metal surface, after gaining sufficient energy, the electron starts emitting from the metal surface. So this is how the classical mechanics will contradict all the observational facts. So hence the classical mechanics will be a failure for the explanation of the photoelectric effect. In the next part of this video, we will be seeing how does the quantum mechanics, okay, we will try to explain all the unobserved phenomena of the classical mechanics, okay. Now in this part, so we will be explaining how will the quantum mechanics try to explain the phenomena of photoelectric effect. Why? Because according to classical theory, that is, if you consider light as an electromagnetic wave, so we have seen that there is a failure, that is, it cannot explain all the observed facts of the photoelectric effect. So now Einstein, what he did, he utilized the Max Planck quantum theory to explain the phenomena of photoelectric effect. So what does Max Planck quantum theory states? That is, it says that the energy absorbed or released will be taking place in discrete packets of energy, that is what we call it as an quanta of energy. So the energy of each quanta is what we call it as E is equal to h into nu, where E is the energy of the radiation and h is the Planck's constant and nu is the frequency of the incoming radiation. So this is what we call it as Max Planck quantum theory. So according to Max Planck quantum theory, it says that the energy emitted or the energy which is observed will takes place in a discrete packet of energy, and that discrete packet of energy is what we call it as an quantum, okay. So now if you consider or if you come for light, this small packet of energy is what we call it as the photons, okay. Okay, so what do you mean by photon? So the small packet of energy that is present inside the light, so this is what we call it as a photon, and the energy of each photon is given by E is equal to h into nu. So Einstein, what he did, so he used the phenomena of Max Planck quantum theory to explain the phenomena of photoelectric effect. So now here, what is light made up of according to quantum mechanics? It consists of discrete packets of energy, that is what we call it as a quanta. So and the energy of each quanta will be given by the equation E is equal to h into nu. Now so discrete packet of energy means it is a microparticle, that means a very small particle, okay. So when this microparticle or when this radiation is made to incident on the metal surface, that is where the energy of this discrete particle, that is the microparticle or the photon, when this energy of this photon is observed by an electron, okay. Electron is also a microparticle and the photon is also a microparticle. Since there is a collision between two microparticles, the process will be an instantaneous process, okay. So in the observational facts, we have listed out that the photoelectric effect is an instantaneous process. Now we know that there is classical mechanics is a failure to explain the photoelectric effect. Now Einstein uses the Max Planck quantum theory in order to explain the phenomena of photoelectric effect. So now what does light consist of? According to quantum theory, that is, light consists of discrete packet of energies. Okay, so discrete packet of energy in case of light is what we call as a photon, which is a microparticle. Okay, since there is collision between two microparticles, one is an electron and the other is a photon, so therefore the process will be an instantaneous process. Okay, now so this explains the first observational phenomena of the photoelectric effect. Now in order to explain the other observational facts of photoelectric effect, Einstein formulated a formula for the photoelectric effect, and that is given by h into nu, which is equal to work function plus maximum kinetic energy of the photoelectrons. So we can write this equation as h into nu is equal to h into nu naught plus kinetic energy maximum, so that is half m v square maximum. So the quantum theory will demand for the minimum frequency of the incoming radiation. That is, for the incoming radiation, we have seen that if the frequency of the incoming radiation is less than the threshold frequency, there is no emission of the photoelectrons. But classical theory says that there is no need of the minimum frequency concept, or there is no need of minimum frequency. If sufficient high energy beam is made to incident on the metal surface, there is emission of the electrons. But the quantum theory demands, or it says that there must be a minimum frequency for the incoming radiation. Now with the help of this equation, let us see, is there any requirement of the minimum frequency. So with the help of this equation, if I take this h into nu naught on the left hand side, so it will be minus h into nu naught, this is equal to half m v square maximum. Okay, so if I pose a condition that if nu, that is frequency of the incoming radiation, is less than nu naught, then here we can see that the kinetic energy, that is half m v square, will be negative. Okay, that is, if you apply a condition that if frequency of the incoming radiation is less than the threshold frequency, so we can see that the kinetic energy will be negative, which is impossible. For an electron, the kinetic energy cannot be negative, but the charge of electron is negative, but the kinetic energy of the electron cannot be negative. So therefore the prediction that there is in the case of experiment, we have seen that if the frequency of the incoming radiation is greater than the threshold frequency, then only there is a possibility of emission of the electrons. So now Einstein uses the quantum theory and formulates an equation, or gives an equation where there is h into nu is equal to h into nu naught plus half mv square, where h into nu naught will be known as the work function of the metal. Okay, so this work function is different for different materials. Okay, so if I pose a condition that if nu is less than nu naught, then we can see that there is half mv square, that is the kinetic energy will be negative, which is impossible. So therefore the quantum theory upholds, or it withstands, or it demands that there must be a frequency for the incoming radiation which is having a minimum value. So if the frequency is less than the minimum frequency for a given metal, there will be no emission of the photoelectrons. So this explains that beyond the that is if the frequency of the incoming radiation is greater than the threshold frequency, then only if you increase the intensity of the incoming radiation, the photoelectric current will increase. So this explains the second observed phenomena of the photoelectric effect. And in the fourth observational fact, we have seen that as the frequency of the incoming radiation increases, the kinetic energy also increases. If you need, you can recall this graph. Okay, for two metals we had plotted a graph, that is for metal A and metal B, by taking the frequency of the incoming radiation on the x-axis, and along y-axis we had plotted the kinetic energy maximum. So from the origin until the frequency of the incoming radiation is less than the threshold frequency, the kinetic energy is 0. Why? Because here we had a function, that is what we call as an work function, that is h into nu naught. So what is this work function? Okay, let us define what do you mean by work function. See, work function is nothing but the minimum amount of the incoming radiation that is being required to take out the electron from the metal surface. So this particular energy is what we called as an work function, radiation. So therefore work function will be given by h into nu naught. Okay. So as the frequency increases, since the work function is a constant for a given metal surface, okay, then so whatever the energy, or if you increase the frequency, what happens? The energy of the incident radiation increases. Why? Because we have E is equal to h into nu. Okay. If you increase the frequency, then since the Planck's constant is constant, I mean Planck's constant is a fixed value, so the energy will automatically increase. So therefore what happens? As you increase the frequency of the incoming radiation, the total energy of the incident radiation increases. Since the work function is constant, definitely what happens? The kinetic energy increases. So this equation will explain the fourth observational fact also. And we also seen that half mv square maximum, that is the maximum kinetic energy is equal to the stopping potential energy. That is, we have seen that as the frequency increases, the stopping potential also increases. Why? Because as the frequency increases, kinetic energy also increases. So therefore we say that as the frequency of the incoming radiation increases, the stopping potential is different for different frequencies. So this quantum theory, or this Einstein's photoelectric equation, will explain all the observed phenomena of photoelectric effect. So how did Einstein formulate this equation? He formulated this equation with the help of the Max Planck quantum theory. So therefore this quantum theory, or this quantum mechanics, will explain completely all the observed facts of the photoelectric effect. So this is how quantum theory overcome the obstacle that was faced by the classical mechanics. So hope you have understood this particular concept. So see you in the next video. Thank you.